Okay guys, let's take a look at our lesson for today. This is a lesson on the chain rule, and this is day 1 of 2. So typically if I spend more than one day on a topic, it's probably because it's a little bit more intense than the other topics. The chain rule, the first time that you learn it, some students have a very difficult time with it, because it's really abstract. So we're going to kind of walk through it really slow and talk about when we would use it and how it would look. First of all, let's look at the situation when we would use it. So this example right here, this is a composite function. You probably remember that from pre-cal, a function inside of a function. That's what you use the chain rule for, is for composite functions, not for functions that are being multiplied to each other. These two are not being multiplied together. They are an actual composite function. So that's what we use the chain rule for, when there's a function inside of another function. And so let's look at the rule itself and try to make some heads or tails of what's going on. So this is what my original function looks like. And when I take the derivative of it, what I'm going to do is I'm going to take the derivative of the outer function. I'm going to copy and paste the inner function. Then I'm going to multiply by the derivative of the inner function. That's, I guess, why they call it a chain. We could think of this as one link in the chain, and this would be a second link in the chain. So they call it the chain rule. Each chain is multiplied. We would multiply them all together. And so that is the basic idea behind the chain rule. What I have done here is kind of pulled something out, a variation of the chain rule, because I found over the years students have a really hard time with this particular concept. And so I'm calling this the power chain rule. It's the power chain. And so the way this one works is there's some function raised to some power. The way the power chain rule works, which is really just the chain rule, but it's a version, is where I bring down the exponent. I'm doing the power rule first. I bring down the exponents right here, copy paste the inside, subtract 1 from the exponent, then I multiply by the derivative of the inside. And that's the concept behind the chain rule. Now it is certainly possible, and we will see more than 2 links in a chain. We'll see like a function inside of a function inside of a function, inside of a function inside of a function, maybe? I don't know, it could go forever. So yes, there is no limit to the amount of links of chain that we could do. I had a student earlier trying to say, what is the limit of the amount? I was like, there's no limit. I don't know. I guess it depends on the problem that I want to give you. So let's take a look at our example. I tried to give you a pretty simple example first. And so we're going to go through this example, and then I want to explain how this particular rule works. So, because I don't have an example for that, I'm going to create one. So the first example, let's look, we have sine of e to the x. Now hopefully you can kind of tell which is the outside function and which is the inside function. That is very difficult for students. It's one of the more difficult things to do as well. Which one is the outside, which one is the inside? And so when students first start doing this, I encourage you to write out which one is the first one and which one is the second one. You don't have to, it's certainly not, I'm not requiring it, but it is a good idea if this is a little bit difficult for you. So the outside function is called f of x, and in this particular case, our outside function would be sine x. The inside function is called g of x in our formula, and in this particular case, g of x would be e to the x. Now, if we were to do a composite function, f of g of x, which you have a lot of experience with from pre-cal, you would simply take this, insert it where this x is, and you would get this function. Okay, so I hope that you're okay with that. But that's basically, sine would be the outside, e to the x would be the inside. So now let's apply the rule. Let's look at this rule. So what it says is, take the derivative of the outside function and just keep what's inside it alone. You can not even look at it, right? Because I know sometimes students want to do something with it. Don't do anything with it. Just keep it inside. So let's do that. So y prime equals, we know the derivative of sine is cosine. So we would say cosine, keep the middle inside in, we don't mess with it. Then it tells me to multiply by the derivative of the inside. So I'm going to multiply by, and we know the derivative of e to the x is e to the x. And so that would be our derivative. Now my recommendation would be not to leave this here. We don't want anyone to be confused and think that this is part of cosine's argument. So I would rewrite it and bring the e to the x in the front. So e to the x cosine of e to the x. And that's my very first chain rule. How are we doing on that? Okay. So what I'd like to do now that we have a little bit of experience with the chain rule is I would like to go back to this one and give you an example. I'm just going to make up an example and I'm going to show you how the power chain rule works. So let's say we have something like this. Say we have something like that. That binomial to the 27th power. That is certainly not something that we would want to write 27 of them and multiply them all out. Although I guess if you don't have anything to do on Friday night, you might want to do that. I mean, I don't know. Write 27 of them out and then multiply them all out. But really, to take the derivative, we would just use the chain rule. I'm going to use the power chain rule. I'm going to do this version right here. So I'm going to take the 27 and I'm going to bring it down front. I'm going to copy and paste what's inside. Then I'm going to subtract 1 from 27. Then I'm going to multiply by the derivative of the inside. Okay, we kind of cleared that. That's how it's going to work. So we would say y prime equals, I'm going to bring the 27 down and then copy and paste what's on the inside. Don't change it, just leave it alone. Subtract 1 from 27 and get 26. Then I'm going to multiply by the derivative of the inside. And the derivative of 3x cubed plus 2x, that would just work that out. So that would be 9x squared plus 2. Notice how, and I've been seeing all day, some students are not putting this back piece in parentheses. It needs to be in parentheses. This whole 9x squared plus 2 is being multiplied by this front binomial, not just the 9x squared. Okay, and that would be our answer. I mean, that's all we would do. There's really no simplification to that. That's as simple as it would get. So that's an example of like a power chain where we have some function to a power. Okay, we okay? All right. So let's do this next one. This next one is actually 3 layers. This one was 2 layers. I had 2 links in my chain. This next one is going to have 3 links. So let's think about that for a second. Okay, I'm going to have the outside, and then I'm going to have an inside, and then I'm going to have something inside of the inside one. Okay, so it's going to be nested. They're nested together, like, I don't know if you've ever seen those Russian dolls where one doll's in the others and the others in the other, okay? It's like we could have a really gigantic, beautiful nest of chain rules. I mean, that would be so fun. Okay, so let's pull it apart, and let's do the outside and the middle one and the inside. So I'm going to call the outside one f of x because that's what this does. So let's get a little bit of room over here. Okay, so f of x in this case is e to the x. Okay, f of x is e to the x. That's the outside function. They're layers. We're basically doing the derivatives of the outside layers all the way to the inside. All right, so the next function, the g of x function, the function that's inside of e to the x is secant theta. That's the function inside of e to the x. The function inside of secant theta, which we're going to call h of x, is 3 theta. Okay, so there's 3 layers here. Now let's talk about that, because this actually, if this was an unrelated problem and I simply ask you to take the derivative of secant 3 theta, what's the derivative of that? Some students would just write down, you know, oh, that's secant tangent, or secant 3 theta tangent 3 theta. We don't have a rule for this. So every time that you're doing the derivative, you have to ask yourself, what is the rule that I'm using? If this does not look like a rule that you know by memory, then you're going to have to do the chain rule. I mean, that's just how it works. If it doesn't look exactly like secant theta, you're going to have to do the chain rule. And that's what's happening here, because it's secant 3 theta. So that requires a chain. So let's work this through. And then I'm going to write a formula for you with the h of x in it. I think that was helping students earlier today, so I'm going to write that formula for you. but let's work through this first. So we would take the derivative of the outside function, which is e to the x. So we know the derivative of e to the x is e to the x. So I'm going to e to the, and I'm just going to copy down what's in there. I'm not going to bother with it. I'm not going to do anything to it. Okay, so that is the first chain, the first link in the chain. The second part is to multiply by the derivative of what's inside, and the derivative is secant. Our derivative of secant is secant tangent, and I've got to copy down what's inside of it. Okay, I'm not going to do anything with it. I'm just going to copy it down. So my derivative of secant is secant tangent. Okay, that's my second chain, so my second link. The last one would be multiplying by the derivative of 3 theta. Now the derivative of 3 theta is 3, just like the derivative of 3x would be 3. Theta is simply a variable, so it's 3. Now I really would not want to leave the 3 here. I would want to pull it in front because it kind of looks like it belongs to this tangent argument. We don't want that, so I'm going to rewrite it, and I'm going to put the 3 in front. So 3e to the secant 3 theta times secant 3 theta tangent 3 theta. Now before I take questions on this, I want to write out a formula that is basically 2 inside functions. So let me do that, and then I would like see if anybody has a question. Okay, so if my function was f of g of h of x. Okay, if that's my function, this is what my formula would look like. Okay, I'll go over here. So f prime of x would equal f prime of g of h of x times g prime of h of x times h prime of x. That would be a formula for 3 layers. And if we had 4 layers, we would just tag on another layer. Okay? So this is what my equation would look like. That would be the composite that I would have. And this is the formula that I would use to generate my derivative. And that helped some people earlier. So questions on this second example? Hopefully this formula kind of helps you with your thinking about where that's going. Yes? Sure. You sure could, and actually we do some on the daily work. You could have a g of h of x inside of here, and with the power rule, you bet. Yeah, there's really no limits. Oh yeah, we could have all kinds of fun going on. And plus the chain rule inside of the product rule, inside of the quotient rule, it's like, oh, I know, it's going to be great. Okay, are we okay with this one? All right, last one. And so let me get some room up here. We need to identify how many layers we have. Again, you certainly do not have to write these functions out. You can just work the problem. I think it's helpful when you very first learn the chain rule to do this. So my very outside function, g of x, or no, excuse me, f of x, we'll use f of x as the outside, is 2 to the x. And I don't know if it was this class that had a to the x, the derivative of a to the x on their formula sheet or not, but we did terrible on this. Terrible. Okay, it's a formula. This is a to the x. The derivative of a to the x is a to the x ln a. Period. There is no power rule with an exponent that's a variable. That is not a thing. The power rule only works with an exponent that's a number. Power rule we would use for this. We could not use a power rule for this. Okay, it's 2 different things. Right? This is a special rule. And actually I'm bringing that up because that's what function is in here. My innermost function here is 2 to the x. My outside function is 2 to the x. The one inside of 2 to the x is 3 to the x. And then I have one inside of the 3 to the x, which would be my h. The one inside there is x squared. So this is another 3 layer or 3 links in the chain. All right, so let's do this one. So y prime equals. Okay, so the derivative of 2 to the x is 2 to the x ln 2. So 2 to the, just copy what's in there, don't pay attention, ln 2 times. The next inside function is 3 to the x. The derivative of 3 to the x is 3 to the x ln 3. So 3 to the, again, don't, just copy what's in there, 3 to that exponent, ln 3 times. Then my innermost function is x squared. And the derivative of x squared would be 2x. Now that particular equation has a lot of stuff going on. I would probably rewrite it to make it clearer. Is there a way that I have to have you rewrite it? No. I just need to be able to distinguish things independently. I don't want, this 3 to appear to be part of the log expression. I just need to know what is what. So what I would do is I would rewrite it. And I would probably put the algebraic part first, the 2x, and then I would probably put ln 2, ln 3, which I could, I would try ln 2, ln 3. Then I would probably put the 2 times 2 to the 3 to the x squared, and then times 3 to the x squared. I think that's kind of clear on each thing being separate and not blended together. All right, questions on that last one? Yes?
For the rewriting, we don't have to do that.
It really depends. If I can tell that, something like this, if I can tell that this is not in the argument, then you could get away with not rewriting it. It's just safer to rewrite it so that I don't misinterpret what you've done. That's all. Yes? Yeah, that is a good way to separate them. You bet. If you put the multiplication symbols, that would be fine. And something real complex like this, that's a good idea. Yes? Or parentheses, sure. That's clearer too. No. No. I just need it to be clear. So, other questions? Yes. Right, it's multiplied. They're just attached by multiplication is all. No, good question, but no, we don't. Because since it's all multiplying, you can move them around in any order you want. Okay, anything else?